So, good morning, everyone. Welcome to the European Quantum Week at schools. My name is Tony Apollaro of the Department of Physics from the University of Malta, and I thank all of you for your participation, for your enthusiasm in, say, connecting online and go together with us in these 2 hours illustration, maybe just scratching the surface or giving the flavor of what are quantum technologies. What is the physics they are based on, and what will be the perspectives and the future of quantum technologies, mainly in Europe, but not only. So I will start with a presentation. First of all, say, I see that you all can hear me, you all can see me and the presentation. And if there are questions or remarks or points, you just write in the chat. So this is first some technical, some say organizing details. This is an event organized by the work group that is the Quantum Technology Education work group of the Quantum Flagship. The Quantum Flagship is a 10 years multi-billion European program on quantum technologies, because the technologies coming from quantum mechanics has already given so many products to our society that it has been termed the first quantum revolution, happening, say, more or less with transistors, lasers, 50s, 60s, 70s. But now you are on the edge of the coming second quantum revolution, because now there is such a level and a knowledge of how to control single quantum systems that people are starting to think how this control can be used for technological devices. And some of them are very astonishing, going from teleportation to quantum computation to cryptography. So this presentation will be mainly starting with what is quantum? So what is the idea of quantum mechanics? Then a brief overview of what we mean by the first quantum revolution. Then what is the second quantum revolution, the era in which we are, and what are their main applications? Quantum sensing and metrology, quantum computation, quantum communication, quantum simulation. Finally, there will be, because it's intended for schools, the technical level will be, say, I hope, appropriate. Then it is interesting to show how this affects you. You are starting your career, your school and possibly academic career, and is there space? What's the space? What are the directions that quantum technologies can offer you? Finally, I will just go to the conclusion. So the length of this session will be more or less half an hour, maybe a bit more, let's see. I already started talking too much, so probably it will be a bit more than half an hour. Then there will be Karl Pelka, University of Malta, a PhD student, that will perform and live broadcast an experiment on quantum cryptography, because of all these pillars of all the quantum mechanics, condensated it in half an hour is absolutely impossible. So we decided to choose quantum communication as one of the points to highlight in this talk. So quantum mechanics, one says, oh, it's such a difficult thing, but it's, where is it? Are we studying something that just came out of our mind without any ground? Well, we have quantum mechanics everywhere, from very small things when one studies the collisions at the CERN of atoms, subatomic particles, and so on. But we have quantum mechanics even in something that governs quite macroscopic bodies. Say photosynthesis is believed to be a quantum mechanical phenomena, or it's coadjuvated by quantum mechanical phenomena. Solar panels, it's based on photoelectric effect. So also there is quantum mechanics. Nuclear power, of course, is quantum mechanics. Then laser, and the experiment that Karl will perform is made with lasers. And lasers are used everywhere, going from measurement to eye surgery. But quantum mechanics is also, thanks to quantum mechanics, integrated circuits comes out. And integrated circuits, then also the cameras, the CCD cameras that you have in your phones, they are based on the laws of quantum mechanics, as well as LED, and of course the origin of the energy that arrives to the Earth and gives life to everything is nuclear fusion. So it's based on quantum mechanics. So even if generally one believes or says that quantum mechanics is the study of tiny, tiny, tiny things, atoms, molecules, electrons, and so on, it actually governs many things around us and has given us very fruitful technology in the past decades. Now we will just show one instrument, that is the laser. Say, how does the laser work? We focus on the laser just because it is the one Karl uses. So a laser is based basically on the fact that there is an atom in which the electron can stay in two positions or in two energy levels. But like a stone, that if you put it here, it goes down. If an electron is a bit up, so a bit more far away, say, from the nucleus, then something comes, and this something is called a photon. So say light arrives, one particle of light, one quantum of light arrives, and it pushes down the electron from, say, one floor to another of the atomic building. And by doing so, we had one photon that enters and two photons that exit, and these photons are identical. So laser is an acronym, and it states exactly as a long description, the word is a long description of this phenomena. It's light amplification, because light comes in and comes out, but it is amplified by a phenomena that calls stimulated emission of radiation. Of course, the word laser, it's more interesting and also shorter, so more useful. So let's see what it means quantum. And our world is becoming quantum. Quantum mechanics sometimes is believed to be paradoxical. Paradoxical in that it gives us a view on the world around us that does it's not easy to put to make peace with it. It's a contrasting with what we think is common sense. And the most famous example about it is the Schrödinger's cat. He had a special cat. And somehow it was a cat that, if the laws of quantum mechanics would apply also to big objects like a cat, then the cat should be dead and alive at the same time, or it should be neither dead or alive at the same time. Now, I will not go into the details of the description. I invite you to show it up because it's a long description, but it is easy. Somehow it says, as in quantum mechanics, an object can be at two places at the same time, then this property of being in two places at the same time from the atom can propagate up to the macroscopic world. So also the lever should be at the two places at the same time. Even the hammer should be at two places at the same time. Even the vial with the poison should be at integer or broken. And so even the cat at the same time has drunk the poison and has not drunk it. And so even the cat is at the same time dead and alive. Now, this is the path we will go a bit through. For this, of course, it's paradoxical because somehow one thinks, but I don't see a cat that is dead and alive at the same time, but we see an electron that is at the same time in two different places. Or we do not see, we see phenomena that can be explained only by saying that an electron is in two places at the same time. So somehow there has to be a border between what is ruled by the quantum mechanics and what is ruled by classical mechanics, like sun, planets, or photons, electrons. And quantum technologies is based on the property to take phenomena, the physics of quantum mechanics, and make it useful for us who live in the classical world, or even to push this border more into the macroscopic world so that we are able to observe quantum phenomena even in bigger objects. Now, what are these quantum phenomena? Well, first of all, a disclaimer. Quantum mechanics here, I collected some sentences of the people who founded, so the father and sons of quantum mechanics. And they said, first of all, when we talk about quantum mechanics, two things are the same object. Well, it's like language can be used only as in poetry, in the sense that when we give a description of the quantum world with the word we have used in the classical world, we talk via metaphors, via analogies. It's difficult to exactly express it in words because there is a mathematics behind, but we will not use mathematics. So we will work with analogies that may not be scientifically rigorous, but they give the analogy. Then, like sentences of Feynman, who says that a paradox is only a conflict of what you think reality should be and what reality actually is. Einstein was one of the opponents somehow of this vision of quantum mechanics because he says that if quantum mechanics is correct, it is the end of physics as a science. Roger Penrose say, all these are Nobel laureates, said quantum mechanics makes absolutely no sense. Wheeler, if you don't understand quantum mechanics, I mean, you cannot understand quantum mechanics somehow. And Schrödinger, the one of the cat, even asks forgiveness for having had something to do with quantum mechanics. So what are these things that change our concept? First is wave-particle duality. Wave-particle duality says that a system, so a system can be a photon, so a particle of light, or a wave of light, but it can be also a cat, or it can be even an atom, an electron. So there is a wave-particle duality. It's a principle of quantum mechanics. And it says that a system is at the same time a wave and a particle. So light is both a photon and a wave. And only when you measure it, when you observe it, you will see it or as a wave or as a particle. So a particle is equal to a wave. The second basic concept in quantum mechanics, that will be the only two we do, is the indeterminacy principle. It says that it is impossible to determine at the same time, see how this always comes, position and momentum. What is momentum? Momentum is mass times velocity. So somehow, if you measure, if you know where a particle is, you do not know anything about its velocity, and vice versa. So somehow, indeterminacy principle is something that tells you there are limits. If we measure the position, so we reduce its indeterminacy in position, then we have a high indeterminacy in momentum. So we know almost anything, almost nothing about momentum, and vice versa. So, and here's the debate. You measure it, but if I do not measure a particle, it has a position, it has a momentum. If I do not measure something, it has a property. And the problem is exactly here. In quantum mechanics, an electron, here on the left you see Schrödinger, an electron is what we measure. There are overwhelming evidence that a quantum object, say an atom, an electron, does not have properties unless I measure them. Of course, Einstein was not very happy with this, and he said, no, a particle must have a separate reality independent of a measurement. An electron has spin location. And here the famous sentence you may have heard. I like to think that the moon is there even if I'm not looking at it. If the moon would be a quantum object fully, under the laws of quantum mechanics, the moon would not be there unless you look at it. Because in quantum mechanics, you have that what we know is what is. So let's see. Here you see just an image of what will be similar to the, because this is of the University of Minnesota, an image of the experiments that we will perform with light, with lasers. So there will be some beam splitters, some polarizers, lasers, and so on. And we see that it can take different paths, the light, but unless we observe it, it takes all paths. This experiment has not done only with light. When I say we are pushing the border of quantum mechanics up and up with a lot of experimental geniuses, this wave-particle duality has been observed even in fullerene. Fullerene is a molecule made out of 60 atoms of carbon. So it's a quite big object, and there are experiments ongoing to see the wave-particle dualism in viruses. So this was for the first principle. Let's go to the second principle, the indetermination. So somehow, if I measure something, say the position, I change its momentum. Now, I will not enter too much into the details because it's also part of the experiment, but a particle has somehow what is called a spin. Spin is, say, the direction along which something rotates. So if it rotates clockwise, the spin is pointing up. If it rotates downwards, the spin is anti-clockwise, the spin is pointing downwards. Now, at the same time, the particle can rotate both clockwise and anti-clockwise. So a quantum object can stay in a superposition of both directions. And if I measure one, I change the other one. So let's make an example, this of quantum mechanics. Suppose you wake up this morning, because we are entering winter, and you want to wear some socks. Socks, not sockets, sorry, socks. So, and you know that you have socks that are red, blue as color, or short, long. So now red, blue, and short, long will be the equivalent of position and momentum, or directions of the spin. So here, you say, oh, you first pick up the color, so you make a measurement. So you have this bunch of socks that maybe are not all placed in an ordered way in the drawer. You put your hands in and you take out all the red socks. So you will have socks that are all red, but which are both short and long, because you have all the combinations, red short, red long, blue short, blue long. So I take the red socks. So I have red socks, all the red socks, which can be both short and long. Then you take, in this bunch of red socks, you take the short ones. Short. So you say, I will put on red short socks. But if you then look at after these two selections, measurement, you look at the socks, you get the blue one. So this is what happens with quantum mechanics. Of course, socks are not quantum mechanical objects, but if I measure one property, here I measured the length, I changed the result, I cancelled the information about the previous measurement, the color. And as information is what an object is, when I go and measure again the property color, I can find the blue one again, even if I can't put them out in the first instance. Now, confused, it can be even worse with entanglement. I will not go too much in entanglement because we will not deal with it. But again, in this discussion between Schrödinger and Einstein, Schrödinger said entanglement is the characteristic trait in quantum mechanics, while Einstein said it's a spooky action at a distance, because it's like I do something, a measurement here, and what I do not change the properties of the object here on which I'm doing the measurement, like happened in this example, where I changed the property of the property of the object that I was measuring. But in quantum mechanics, you change the property of an object that is not the one that I'm measuring. So I have two objects that are entangled. I measure one of these objects and I change the properties of the other one. So just to make an example, suppose we have coins of, say, €2 coins, and each pair of coin is entangled in something that is called a bell pair. Let's not go to the details. I flip a coin and I get tail. Then the other one that in the meantime has taken the second coin of the same pair, and has gone, I don't know, to the United States, flip the coins, and it comes out tail as well. I have one coin here. I flip the first coin of the second pair, and I get head, because I don't know my outcome. It can be 50% tail, 50% head. But after I have make my measurement, the other one, it can be 10 years later, it can be in a different on a different planet as well. He will get a correlated result. He will get head again, and so on and so forth. So the measurement I made on my coin, that is one of a pair, influences a measurement done in a different place in a different time, because somehow we cannot attribute properties to an object prior to a measurement. Now, there are some interpretations of quantum mechanics, but I will not go here into the details. Somehow, there is even a many-word interpretation that says that when you make a measurement, if you have two possible outcomes, like with the head and tail, then if here I got head, another universe opens in which we get tail. So if you ask a boy or a girl to go out for a drink, don't worry, even if he or she says no, because there will be another universe in which she said or he said yes. The important thing is that you are in the right universe. So confused, clearly confused. But all this, that is the physics, the principle of physics behind quantum mechanics, has given us the transistor, has given us the satellites, nuclear power, bar scanner, lasers. These are the principles on which these objects are based in the nuclear magnetic resonance. It's a quantum mechanics effect. And even your phones clearly are based on this science, on this physics. What happens in the second quantum revolution, the one which we are living? Well, there is the quantum flagship, for instance, which is a 10 years long project in which there is a study of basic science, the principles that we have seen, and then the four pillars: communication, computation, simulation, sensing, with several levels. And the aim is to go over the 10 years to have some interesting technologies. We will say, one of which you may have heard is the quantum computers, quantum processors. Other is to use the quantum internet. So here, quantum credit cards. So this is more or less the timeline on which we are going. There are already quantum links there has been sent a satellite in space, and there has been teleported photons over the satellite in space between China and Austria. Now, we will deal with quantum cryptography. Basically, and we now entering, what is cryptography? Cryptography is a way to encrypt a message in such a way that even if someone intercepts your message, he's not able to make any sense out of it. And you use cryptography, we use cryptography every time with the internet. For instance, in the internet, you ask for a public key with which you encrypt your message, and then the server decrypts it using a private key. So there is a public and a private key. And this is the system that is used nowadays. So somehow, other systems more symmetric, you can have a public and a private key. They encrypt it, each with the public and private key, and then it can be used to decrypt. Now, why do we work on cryptography? I mean, there is already a system. The RSA mainly is used on the fact that finding the prime number, so finding the numbers that factorize a large number, is very difficult. It's technically, it's say the complexity is very high. So if I give you a number with hundreds or thousands of figures and say find the factorize that number, I mean, it's not easy. Say if I give you 15, clearly it's 3 and 5. If I give you, you know, 25, it's 5 and 5. But if I start giving you higher numbers, then it's difficult to find the prime numbers, so the factorizing number. So the security at the moment of the cryptographic system is based on a computational complexity. So it's mathematically improbable that you will be able to crack this number. Of course, you need powerful computers, and if quantum computers come out with more qubits than are now, with more computational power, then classical cryptography can be broken quite easily. So we need a different system to encrypt, and this system is based on the principles of quantum mechanics. One of these is in the indetermination principle. So because it's a principle, the security is not given by an improbability, but it's given by an impossibility. So it is not mathematically improbable to crack a cryptographic message, but it is physically impossible, even with the most powerful computer. So the quantum key distribution system works more or less very similar to what we have seen. We have a key, we encrypt a message, we send it, and it is decrypted. So there are many protocols. Some are based on the Heisenberg Undetermination Principle, some are based on the entanglement. We will deal with the PB84 protocol. That is a protocol using photons and using the Heisenberg Indetermination Principle. For this, we need to see what is the polarization of an electromagnetic wave. Now, an electromagnetic wave, as it says, is a wave. It oscillates in the space made out of an electric and a magnetic field, electromagnetic. But we will deal only with the electric field. So it is, the polarization is the plane on which this wave oscillates. If I have, and we are here only considering the electric vector, if I have, say, natural light, the polarization is in every direction. So you have a wave both like the red, the orange, the violet. It oscillates in every direction. What we can do now is to measure. What is measuring? It's using a polarizing filter. So somehow a grid, and the waves that are not in line with that grid do not pass. So I can use a polarizing filter and get only wave polarized vertically. Here we have two filters. If I have, say, a parallel filter like here, and then I put another one parallel, of course it passes again. But if I use now the vertical, so I have the filter and I rotate it by 90 degrees, then it does not pass. And here everything is dark. And we will use aligned polarization filter for our experiments. Now, here's an example. If we take our sunglasses, with sunglasses, you can do polarized sunglasses. You can do exactly these experiments because each lens of a polarizing sunglass is exactly a polarizing filter. So if you use light that comes with all possible linear polarization, two filters that are aligned with the same axis, that component passes. If I use orthogonally aligned, then nothing passes. But I can rotate this by an arbitrary amount. So if I rotate it by, say, 45 degrees, then half passes and half is blocked. Because I don't know if you have made vectors. I can write each arrow like a vector with components. So what is the component of this vector along this axis? And it is, in this case, say, half of it, and it passes. And you can see it with sunglasses, because you see here it's totally black, because it would correspond to this situation. Here probably to this situation, and here probably to this situation. Good. Now we are going towards the last, more or less last part, and we see that the basis. So what is the basis? Basis is how I use my polarizing filters. And what is the message that I need to send? The message is or 0 or 1 because I send bit. So I can use the polarizer or put in this way and this, or rotating it. And so we have that if I use this rectilinear basis, if something passes when the filter is put in this way, means in this way, then I call it 1. If something passes when the filter is put in this way, I call it 0. Then I use the diagonal basis, so another basis in which I measure, which I rotate by 45 degrees. So if something passes, so I detect light after having put a filter in this way, I say 1. If I do not detect it, I would have detected it if it were in this direction. And I call it 0. And you see it from here. If here no light comes out, if here no light comes out, it means that the light, when coming towards this filter, was in this direction. So here I do not detect anything. So the light was vertical, and vertical is corresponding to 1. So I put these numbers. So with this, we will go to the BB84 protocol, but we can do the simulation a bit later because I'm probably running a bit late. And I invite you here to see this kind of simulation, which I will go further on. Now let's go to the last part somehow. So what is your role in all these activities? Europe. In Europe, we need, in order to develop what we are talking about, the sensors to detect the photons, the quantum computers, the simulators, we need students to study physics, chemistry, biology, engineering, mathematics. We need technicians to build the devices. We need to put them on the market. We need to talk, to communicate the science, and we need to implement them in our culture. So basically, we need you. And if we need you, not only quantum technologies and Europe needs you, but also the Department of Physics, or you need the Department of Physics of the University of Malta if you want to pursue a career in the quantum technologies. Here, this is the Department of Physics of the University of Malta. Professor Andre Schwereb is the head of the department, and it's one of the 6 departments of the Faculty of Science, and it's quite old because it was founded in 1915, and at a certain point it had great numbers, always very good and brilliant students. It was split in the Institute of Space Science and Astronomy and Department of Geosciences, and then there are several 3 and 4 years undergraduate programs. Of course, we do not do only quantum mechanics. There is a highly interdisciplinary team. Say, there is an area of research that is electromagnetism, headed by Charles Sammut and Lutz. There is astronomy and astrophysics, Christian Zarbardami and Joseph Caruana. Then there is the instrumentation part, Louis Zamit Manjon. And then quantum optics and condensed matter, in which there is the field of quantum information, on which we mainly we're talking about, but also quantum optics, clearly, if we use light for encoding the information. And this is Andre Schwereb and me. There are several programs, both 4 years Bachelor in Science with honors, medical physics, computational physics, and science for communication is 3 years. And from next year, probably there should also start a 3 years BSc only in physics. And just to say that if you will choose physics in your future, you will be in good company, because we are having very high numbers in the last years. Good. What is the research that is done at the Department of Physics of the University of Malta exactly in this field? Here, this is an article, you know, in Science you publish article on journals that are peer-reviewed and so on. This is on a very prestigious journal, and you already recognize all the work which we have talked about. Polarization, entanglement. So it has been, entanglement has been used to so polarization has been used to entangle photons. Then QKD, quantum key distribution. So there is an optical fiber, 96 kilometers between Malta and Sicily, and it has been used with these devices here, laser, lambda plate, half plate, polarizing beam splitter. You see, all these instruments, and then the receiver. You have Alice and Bob, sender and receiver, to send a quantum cryptographic key. So this is the group at the University of Malta. This is me, the group leader, then Elif, postdoc, science communicator Daniel, Claudio has completed recently his PhD, Mirko is a PhD student, and here we will have Karl Andreas Pelka that you will see soon. For the next if you're interested in what we were talking about, I can say some readings. Alice in Quantum Land is a very nice reading about quantum mechanics with the language of Alice in Wonderland. Programming the Universe is a book by a quantum computer scientist, one of the founders of quantum information. And then Anton Zeilinger, Dance of the Photons, is one of the main experimentalists and other theoreticians that works in Austria with photons and makes a path from Einstein to quantum teleportation. So with this, I have, finished my part. Probably it was too fast, or I said too many things. Okay, I said too many things altogether, but we will have time for our question and answer part. Now, what I will introduce briefly in the last 3 minutes I will talk about is it here? Share. Here is the experiment that will be shown. Here. So you can see the the slide. Here is a link. This is done by the St. Andrews University in UK. And here's how we distribute a quantum key with which we encrypt a message using polarized photons. So there is a photon source. Okay, this we will see the experiment live. Let's see what happened. So it's clear measurement. So I send a photon, Alice sends a photon, and it is vertically polarized. So as we have seen, this corresponds to the value 1. Then Bob, which does not know how to orient its polarizer, it orients it randomly, so or in horizontal vertical or in the diagonal basis. So or like this, 45 degrees. He detected a photon. So the photon passed. So Bob thinks, Alice may have used the same basis because I see it. If they are in the same basis, it passes. And so he says, yes, 1 as well. Second, same basis here. So horizontal was equal to 0. Bob randomly has put horizontally as well, and it was 0 because he detected it. Let's go to this one here. Let's see here. Now, this is an interesting case because this is 1 because it's oriented 45 degrees, it passed. Bob as well 45 degrees, you see this here, but say oriented along the other axis at 90 degrees with respect to this. So it did not pass. Now, Alice had put 1. Bob has put 1 as well because the photon did not pass. So Bob says Alice has used the opposite. So the 90 degrees orientation. Otherwise, it would have passed. Here, we see 0, because this was the 0 with the 45 in this direction. Here, he did not use it. He did use the horizontal, did not detect it. So he says, Okay, this is oriented upwards because I did not detect it, the Alice's polarizer, so it has to be 1. Now let's look, no, let's go fast forward 100, and we see here some situation. What is the key? The key is a string of numbers, a string of bits, a string of zeros and 1. When do we have the same basis? Yeah. Then I can use the key. You see, here both got 0, 0 and 0. But this 0 and this 0 are along different bases. So they cannot use it because they will, when sharing the key, they will communicate the bases. And they will take only the bits that they got out corresponding to the same basis, like here. Now, why this is absolutely secure? Let's put an eavesdrop. Say, well, cannot someone intercept a message? I intercept a photon, copy it, and send it back, so I have the same numbers. Well, in quantum mechanics, there is a no cloning theorem. You cannot copy a photon. You cannot make an identical copy of something. It's not like in classical mechanics. The information contained, say, on a sheet of paper, it can be photocopied, and you have two that are identical. In quantum mechanics, there is no photocopier. You cannot copy, cannot make an exact copy of something that you do not know. In classical mechanics, you can. You have paper, you make you don't read it, you make a photocopy, and I mean, you have copied information you don't know. Here you cannot. So let's see what can an interceptor do. What an interceptor can do is, an eavesdrop, I intercept the photon, but by intercepting a photon, measuring it, I destroy it because it leaves a spot. It's destroyed. But I can generate another one, like the one I think Alice has sent. But if I go fast forward and then we see, you see, here we, in this case, error. In order for Alice, for Eve to be able to intercept the message, Eve should always choose the same basis that Alice has chosen, but Alice chooses randomly and communicates only after the measurement done what basis she chooses, because if Alice chooses, say, the horizontal vertical direction, and Eve puts the 45, then when Bob chooses the same basis as Alice, because Eve has made a measurement, Eve destroyed the photon of Alice. So when it goes, when it sends another one, the measurement that Bob does can be a different number than Alice. So when then they use Alice and Bob, how does now the key work? Alice and Bob said, these are the bases we have communicated, and for, say, 100 numbers, they say the first 10 numbers, the outcomes. If they have the same basis, like here, okay, let's make another here. Okay, like here, they have the same basis and the same number, then they say, okay, I can use it as a key. But if they have the same basis, like here, and a different number, then they know that someone was there trying to intercept the message. And they decide to not use the keys they have generated because there was someone intercepting. So they can, and they repeat the protocol until they are sure that no one intercepts. So this will be, I talked for probably too much, this will be the content of the experiment by Karl. If so if there are, well, I guess there are many questions in this this part already, but we can deal with it and if there's time for the question and answer, or just contact the Department of Physics for this or we can contact the Department of Physics for the curiosity, if go for research starts on, or make an internship. So with this, I pass the ball to Karl, Andreas, Pelka, who worked a lot in the last months to set up these experiments. So thank you for your attention in the meantime and listening to what I said. Go ahead, Karl.
Then I will take over. Can you hear me first and foremost?
I can, yes. I unmute myself and I put away my video now.
Yes, that's great. So good morning, everyone. So thanks, Tony, for the theoretical introduction. So what I want to do is I want to show you the lab first. So I have a few cameras. So let's do something after the talk to free our mind of what Tony just said. So a short tour. This is actually the lab where the QKD experiment was done. So you get an idea of what a physics lab looks like. So we have the tables where this is going to be Bob, but I will also show it in the presentation a bit more clearly. We have.
So, sorry, Karl, we don't see the table. I think you're on the other camera. I see the door.
Okay, so let me block out that camera for now. So there's multiple cameras going on at the same time. So maybe it makes sense to only switch on the cameras which are relevant. That's okay. So again, this is now going to be, this would be your workplace if you were able to come here. And this is our optical table, but we will also go more into the details, what's on the table in the presentation.
Karl, I'm sorry. Yes. I think again.
You can click on the screen where I'm talking. So you just need to click on the video, and then you can change whichever screen you are actually looking at.
Okay,
that's also maybe good for, yeah, that's also good for the audience to know how to how to navigate. So a new experience for every one of us. So I set up this camera, and probably you should now change to the other, where I'll be waving in just a second. Hello, everyone. I'm on this camera right now. And let's maybe start now with the presentation. Okay. One short question. Can you see my mouse pointer? Because I will point throughout the slides all the time. Tony, can you give me a yes?
Yes, yes, I can see it.
Yes. Great. So, yes. Perfect. So what I want to talk about, I want to pick up where Tony left off. So what we want to do is we want to communicate secretly. And we want to see how quantum physics will help us. Okay, so for that, I want to talk about secret conversations, because since you are students, you might think, so I want to have your opinion. So who keeps secrets usually? If you want to, you can give me some input. Who do you think needs to keep secrets? Okay, so if no one has an idea, so you might think that usually the military or governments need to keep secrets, right? Because if there is, for instance, war times, you can imagine that they sit around such a desk in a war room and they need to make up some tactics or some strategy, and the enemy should not know that. And that's basically 90% of cryptography, say, until a few hundred years ago. But opposed to that, actually, you, and I talk to you as the students, you also need to keep secrets. So, but how come? So this is something that actually happens. So my wife is an English teacher, and so in German this is called, what you see as a teacher is you collect the books where the students write the homework and the teacher corrects it. And if you see something on the sidelines where students just draw some drawings or they draw whatever comes to their mind, this is called the blossom of style in German, Stilblüte. And this is one of those, a very beautiful one, where one student tried to scramble. So he had a message which he had in his mind, and he tried to scramble it just by crossing it out. But he crossed it out very bluntly, not very elegantly, because if you actually look at it, there is still the message left. And it's not an entirely nice message, but so be it. So we have all messages, or we have thoughts in our mind, which we better keep to ourselves or to the audience, which is okay with it. So we all need to keep secrets in some way. And also a nice way how we can see that we all keep secrets all the time is so that's for me. So you would also think that usually if you go to a bank, they should keep secret what your credit card number is and so on. Whenever you connect to, I go to the Bank of Valletta, whenever you connect to it and the message says HTTPS, this S stands for secure transmission. And if you look into the certificate, you can inform yourself how actually it is encrypted. So you can make sure that there is some procedure going on that actually I'm talking to my bank and actually no one else can listen in. So, okay, so this is every day. We use it every day, we need it every day. And now the question is, how do we keep messages secret? And I will just show you a very nice message, and it's scrambled. It's much better scrambled than the students' scrambled message, and you might not understand it. However, we will now use so as I said, cryptography is very old, and it was usually used for military purposes. And we go into the very basic, one of the very first documented uses of scrambling messages, namely Julius Caesar. This is a Caesar cipher wheel, as it's called. And how it works is documented already by old, by old historians. And he says about this, Suetonius says about the Caesar cipher that if Caesar had anything confidential to say, he wrote it in cipher. That is, by so changing the order of the letters of the alphabet that not a word could be made out. So a scrambled message. If anyone wishes to decipher these and to get at their meaning, he must substitute the fourth letter of the alphabet, namely D, for A, and so on and with the others. So we shift every letter in the alphabet by 3, so to say. So, and if I do this with the message which I showed you earlier, and I don't do it with every letter, but I only do it with the 8 most common letters in this message, we get this. Okay. Maybe to the Maltese students, this should already resemble something. And so what I also want to tell you is I only choose the 8 most common letters, and it so turns out that those are also the most common letters in the English language. So this is basically how we can always attack this cipher. If we look at this message and we compare it with the Maltese anthem, with the English part here. So guard her, O Lord, as ever thou hast guarded this motherland, so dear whose name we bear. Keep her in mind whom thou hast made fair. Well, I mean, that's the problem with this cipher. that already knowing a few letters will give away the rest of the message if you interpret it. Okay. So we can use a Caesar cipher to scramble messages by sharing one shift distance. That's what we did for now. And we call this the key. However, in order to do some safe way of encrypting messages or scrambling, we should probably use a shift distance for every letter. And this is proven to be actually safe. Okay, but that's so far for now. So we can translate the problem of secret communication into secretly sharing shift distances, which we will encode in zeros and ones, as Tony already told us. And maybe I give you one brief moment to let that sink in. If you have any questions, let me know. If not, I will take 20 seconds and then move on. I don't see anything. Okay, so then let's move on to the next part where I want to discuss or repeat in a different way what Tony told you about photons or about light. So Tony told you already that photons are the particles of light, and then there is this wave-particle duality. But let's start with the wave part. So how did photons come about historically in the history of physics? In the late 19th century, Heinrich Hertz was a PhD student just as I was. And in his experiments that he conducted for his PhD, he found out that electromagnetic waves, so he could produce electromagnetic waves by sending currents. And he found out that these electromagnetic waves travel at the speed of light. And from that realization that this speed is exactly the speed of light, it was deduced that light is actually electromagnetic waves. Okay, so let's talk about waves. So which waves are the most common ones for you Maltese students? So since we live by the sea, probably water waves are very common to us. So just a nice picture. I wonder where you have such facilities, but okay, interesting. So what we understand as a water wave is how the surface of the water moves with respect to no movement at all, right? So if you follow the red dot on the right-hand side of this picture, this red dot moves up and down because the surface of the water with respect to its mean value or the mean height of this water is deviates. Okay, and one other thing that we should mention is that the wave travels here, say in this direction, and in the right-hand picture from left to right. But the motion of this red dot is in a direction which is perpendicular to it, up and down. Okay, and that's what we call transverse waves. And it turns out that the same holds also for light. But now since we have a light beam, we have a one-dimensional object. Maybe I probably won't show it the laser pointer, but you can imagine a laser pointer, and a laser pointer gives you one beam of light. Since it's more or less a one-dimensional object, we can understand that there are now two perpendicular ways that the light can also, or that something can oscillate. And one is, so to say, this type of horizontal oscillation of the electric field, as Tony said already. And then we also have the vertical oscillations going on. That's also perpendicular to the propagation direction. Okay. And as Tony told you already, we can have different bases and more complex ways how what we call then the polarization can be aligned. So we had already the 45-degree basis, but so usually regular light, which does not come from a laser pointer maybe, it is completely unpolarized, so there's a bit of everything. And as Tony told you, we can block out, so this is maybe the more physical realization or of a polarizer, because in Tony's way, or in Tony's more didactic representation, the grid always goes like a sieve. So it goes, the light goes through a sieve, and this is the more physical representation, but we can talk about it later. Doesn't really matter. What we understand is that one part of the light or the polarization can be blocked out. And after this polarizer, we know for sure that the light will be polarized in one direction. So this is, this is a part of the indeterminacy principle, as Tony called it. So before we had some knowledge, or there were more bases going on, and with the measurement we destroyed some knowledge or some part of the state, and we have a new state about which we know what we measured. Okay, so maybe let's start with a first experimental demonstration where I will show you that a laser pointer will generate linearly polarized light. So we expect that if we turn a polarizer, we should make light vanish or block out. If the laser pointer actually generates linearly polarized light. So I give you first, so this is a photo of the setup, and we are just working with this part for now, where we can zoom in. We have our laser pointer. I let it pass. No, I will actually not let it pass through this object. I will screw it out, but we have a polarizer, which I can rotate with the computer by means of a motor, and then I will place you in a nice position so that you can see the spot of the beam on the wall. So let's stop the talking. Let's do some experiments. Probably now it's time to switch the screen to the one where I'm waving at you. Hello, hello. So I can also show you that part of the table. So what you see now is this laser beam spot. If you look in the right, so where I put the X in my presentation, this is the laser beam spot where I'm pointing at right now. And what I can do is I can turn the polarizer with my program. Let's see. So we see some light now. And now the polarizer should turn by 90 degrees, which it does, and we have a bit less. Okay, but it's not perfectly aligned. Yeah, maybe something here. Yeah, we basically blocked out most of the light right now. Oh, yeah, but the problem is that I need to turn out the magical object in between. So now we see nothing. I hope you agree. Okay, now again, I turn to another position, and we should see that the light should come back. And just as a maybe other setup where you can believe me that all the things are happening at the same time, with this setup, you should see everything happening at the same time. So now I switch to 65, and the light is gone. Okay. So let's call this the first experimental demonstration. Yeah, I can actually leave you here for now. And now I hope that you switch back to the screen with the presentation. So I give you a brief second. So what we saw is that either by turning the polarizer, part of the beam, or the beam will pass the polarizer, or it will be blocked out. Okay, but we also saw that I can have intermediate angles. And if we have intermediate angles, as Tony already said, we have this thing called vector addition, which I can briefly explain to you here. So if we have parts of both polarizations going on at the same time, what we need to do to get to the final polarization is we need to take, say, the blue part of the, or this blue polarization part and the red polarization part, and we take the beginning of the arrow, we align it to the tip of the other arrow, and then connecting the beginning of the first arrow to the tip of the second arrow gives us the final the final arrow where the polarization is actually pointing to. And this is an animation. So if we have two polarizations going on at the same time, it's the same as having the vertical polarization. And that's also already pointing towards the superposition principle, which Tony also told you about. That this, if we have the vertical polarization, it's partially the horizontal. Right now, if we have diagonally polarized light, it's partially horizontal and it's partially vertical. Okay, we can also have that these partial waves, they point in different directions. If one part changes its direction, we get the anti-diagonal. So here it's the red with respect to the earlier image. Now the red is inverted. And if we do the same addition type, we get anti-diagonally polarized light. And again, we could say now that this is, so if we started with the green as the basis, so this anti-diagonally polarized light is partially horizontal and partially vertically polarized. Okay, and then we can even have a more complicated realization, which is important for the experiment, namely what happens. So here we saw that a maximum of a blue of the vertical polarization coincides with the maximum of the red polarization, of the horizontal one, but they could also be shifted. So in the next case, we have that a maximum of the blue of the vertical polarization corresponds with a minimum or a zero oscillation of the horizontal polarization. And if we look at what's happening, now the light field is turning, this is anti-clockwise. Okay, and if the phase relation, so if the blue, the minimum of the blue coincides with the maximum of the red, then we get clockwise orientation of our light, of the polarization. So why am I talking about this? The point is now these polarizations, these circular polarizations, will be a third basis in our experiment. And this is an experiment we can easily make circularly polarized light by introducing what's called a lambda quarter plate, a quarter wave plate, which does exactly that. So if you look here, we have the alignment of the maxima, and a quarter wave plate will take only one of those and shift it by a quarter wave, such that a maximum is now aligned with a zero, with a node. So what I will do now, I can show you the quarter wave plate. So this is what a quarter wave plate looks in the experiment. It's basically some sort of glass. And if you look more exactly on it, it has, it says, now I misaligned the laser, but okay. It says something about a fast axis, and this will be the axis that will be shifted by the lambda quarter. Oh no, I've completely misaligned the laser now. Great. Okay, let's move on. So what I need to do is I need to put in, okay, we'll check for that later. Okay, so now the light passes through the quarter wave plate into the polarizer, And then again, with the beam splitter, we see it partially on the wall. And you trust me now that the polarizer moves actually if I use my computer program. So what I will do is I will put you more closely to it. And the question now is I need to choose the fast axis very well. Let's see if I did that. If that is the case, I can rotate the polarizer and the intensity of the light on the wall should not change dramatically. So let's see what happens. Okay. Could be better. Okay, so I have 0, and if I turn by 90 degrees, we should at least see once. We saw once vanishing, but that's more because the polarizer is dirty. Let's turn to another 90 degrees. Let's see what happens. Yeah, now we had 90 degrees of rotation. So at one point, actually, all light should have vanished for linearly polarized light, but that didn't happen now, which is an indicator that we actually have the circularly polarized light. I hope you agree with that. You can see the spot on the screen. Okay. So maybe for now, I move you back. So now we know that we can, so let's move back to the presentation. So what we know now is that we can use a quarter wave plate to convert linearly into circularly polarized light. I hope you trust me with that, because after the rotation, we still see light, although for linearly polarized light, we don't expect it because of this quarter wave plate. Cool. So let's put it in a nutshell. So light sources, if you want to characterize light, it may come with 4 defining properties. One is the propagation direction. So if I widely swing with my laser pointer, I can change the propagation direction. It comes with a wavelength, which we perceive as the color of the light. So I have a green laser, which emits light at 532 nanometers. That's the wavelength. Then we have this polarization degree of freedom, which we just experienced. You experienced it now through the camera, but we can also experience it live. And with an intensity, we can see that we can make light vanish or we can make it more strong. Okay, but now what are photons? So photons are now the minimal package that we can have of such an electric field. So maybe a nice imagination is that we have these tiny wave packets where we have like light traveling, and then we have a bit of it at one point, at one instance. And in order to go from this mini package to such a classical field, we need to send a lot of the photons at all times. Then we get like the sum, again, this vector sum. So they would amplify each other. Okay. And the same holds for the circularly or circular polarization. We can also think that a classical light field, so I put on the animation already, consists of many, many minimal packages of such minimal wave packages of such circularly polarized light. And these minimal packets, this is what we call the photon. And these come now with, say, 3 properties: the propagation direction, the wavelength, and the spin. So here we see something spinning, here we don't. And we see that we can imagine that the intensity comes about from having many photons at the same time. Okay. Now let's go back again into the quantum properties of photons. So a revision of what Tony said. The most important thing for our experiment now is the collapse of the wave function, because measurements in quantum systems occur by interacting. So we cannot, as Tony said with the moon. So whenever we look at the moon, actually what is happening, a bunch of light from the moon comes to us. So actually, if we are very serious about it, there is some underlying interaction. So light had to be sent out, and it had to arrive in our eye, and it had to make some currents flow in our brain. So there was actually some interaction going on. And in quantum systems, moreover, we see that we alter the state. That's also what Tony showed you with the polarization, because after the polarizer, we are certain that we have this or that polarization of the light. So in the process of measurement, some information of the state will be lost. And this is also the key why an eavesdropper cannot send the identical photon again, because he lost the information of the basis by measuring. Okay, and now in our experiment, we will have 3 bases, namely the horizontal and vertical basis. Then we have this diagonal and anti-diagonal, which is in some sense a sum of the first basis. I have to go through the animations. And then we have the third basis of the circularly polarized light. Okay. And the important thing about this BB84 protocol is the following, that whenever we measure a photon which is in one basis state and we measure it with respect to another basis, so the photon has a 50% probability of being blocked or a 50% probability of passing. And afterwards, we destroyed the information about the old basis and we imprint the new basis onto the photon. Okay. Again, I want to stress that this loss of the basis information will be what makes the key secure. And also that we use it with one photon, with single photons. Okay, why am I talking about these many bases? The thing is that the circularly polarized light was easy to generate. I just screw in this interesting type of glass. I have to go through the animations all times. And the measurement can be done easily in the first 2 bases. We can just align the polarizers, as I showed you already. I can write a program and I can have a motor which then makes the polarizer turn. And we can use, and we can even have 2 bases which we can measure easily. Great. So I just want to go through one example again to have the idea of what's happening. So since we have a laser pointer, we are not sending single photons, but we send many photons. So we can imagine that we send 100 photons at a time through this lambda quarter plate. So we have circularly polarized light. We say the plus polarization, for instance, which is the, let's see, oh no, which is the anti-clockwise polarization. And we then choose the polarizer to be in the anti-diagonal position. So we measure the anti-diagonal component of the photon. So since we measure in a different basis, based on what we learned so far, we expect that we should on average have 50 photons, which are now certainly in the A polarization. And if we now continue to measure the H polarization, which is in another basis, we expect again to every photon, so this classical beam of light now consists of many photons, of 50 A photons on average. And from these 50 photons, everyone has a 50% of chance of passing or being blocked. So after the second measurement, we expect that we have 25 H photons. Okay. Again, so if instead in the second measurement we chose to measure anti-diagonal, you can see it here in the reflection. So here it goes this way, and here it goes 90 degrees rotated. We have the 2 different ways of measuring in one basis, and we would expect no photons. And okay, no photons are also no d photons. Great. And again, if we measured the same again, if we measured the A basis or the A component again, so every photon will pass. So we still have 58 photons. Okay, so again, a short break to let the information sink in. Feel free to write any comments. Tony, can you look in the chat if there are any comments? Or feel
yes,
free to unmute.
I'm here at the moment. No, I don't see comments, but it's because it was perfectly fine. And even with the experimental
demonstration
lasers, that always happens in a lab.
Yeah. So there's also like a nice saying in German when you talk about, so if there are students which are not into the sciences and they cannot understand what's the difference between chemistry and physics, and then the saying is chemistry is when things explode and smell, and physics is when the experiments never work well. So I'm pretty happy that things work out. So far so good. So then let's move on. So what I want to do with you now, so now on the internet, but let's share a secret with photons. And how are we exactly going to, well, what is our goal? Our goal is to use the Caesar cipher to encrypt securely if Schrödinger's cat is alive or dead, because Tony told us already, it's a very complicated matter. We never know if it's actually alive or dead. So actually, it was planned that someone of you would take the role of Bob, but unluckily, it's me again. I have to play Alice and Bob at the same time. Again, something very quantum, but it's a bit disappointing, but these times are disappointing to all of us. Okay, let's look at this part, this enlined part of the experiment, where you already know this part. This is the laser pointer. We now have the quarter wave plate to get our plus or minus polarized light. We have one polarizer for Alice. We have a polarizer for Bob. And Bob has a photodiode with which he can read on the power meter. Or moreover, it is connected to the computer, so he can even look at what's happening directly on the computer. We call this part of the experiment the quantum channel, because that's where we are sending, or where we are doing the, where we are sending photons with the quantum information. And we have the other part of the experiment. I maybe show it to you in the computer for a moment, for a brief moment. We call this the classical channel, because here we have an infrared sender and receiver on both sides, and they go to the computer so that they can chat. So because we are online now, we can also chat online, but that's not, so to make it more, so to make it even work, if the internet is not here, we could even chat without, so via the infrared, and I will show it to you. Okay, this is, okay, here we have the infrared receiver. I hope you can see it. And here we have the infrared diode. They are hooked up to sources, to electrical sources, so they can actually send something. And it's hooked up to my microcontroller here, so that I can send pulses in a way that we can use it for communication. So maybe let's put you back here, where you have the best overview of the lab. And now it's probably again time to change to the presentation, or to the computer with the presentation, because what I want to demonstrate, it's also intermediate step, is that the chatting actually works via the infrared. So it's also a test for myself. Yeah. All right. Alrighty. So I'm sharing again on the one computer, and I will also start sharing on Bob's computer right now. So you should be able to see everything. Does it work? Can you see both screens at the same time somehow?
Yes, I see. I mean, if I pin it to the screen, I can see both of them. One,
Okay.
the other, yes.
Okay, so let's try out the sending. So let's see if I can chat. So Bob is ready to listen in. Let's see if Alice has something to say. Hi, I am Alice. Let's see if it arrives in Bob at Bob's computer. Hi, I'm Alice. Cool. So Bob can send the message now. Hi, Alice. I am Bob. And let's see if that works. If that is the case, then the classical channel is set up and should work. Hi, Alice. I'm Bob. Great. So we can quit the program. So we know now the classical communication is set up. See, it's also, so also this demonstration is not so, it's good for me in one way because I have to run through the lab all the time and it's some physical exercise, but it would also be much more fun if I were able to do it with one of you. Okay, so our goal is to to see if Schrödinger's cat is alive or dead. And now the question is, since we want to do it securely, and maybe the conversation should go something like this. And if you look in the presentation, so we saw that Alice introduced herself and Bob replied back, and then Bob asks, "Hi Alice, is the cat alive or dead?" And so she wants to say, Bob wants Alice to send an A if the cat is alive, or a D if the cat is dead. But then, since we want to encrypt it, what we will actually get is something more like the cat is G. Okay, but we don't know what G is unless we know the key. So to encrypt this one letter A or D, we need to share actually a 5-bit key. And I will go with you through the details why we need 5. In 5 bits, in 5 zeros or ones, so in the 2 bases, we can encode 16 plus 8 is 24, 28, 30, 31. We can encode all numbers from 0 to 31, or either said in other words, we can encode every shift of the alphabet because we have in the English alphabet 26 letters. So, and in this example of the 10110 key, or the 22 key, as we would call it in everyday life, we would shift an A to a W and a D to a Z. Just a small example, because going 22 places in the alphabet, from the A we will get to the W, and from the D to the Z. All right, so what we will now try to do is we will try to send 16 photons and use the last 5 bits. So as Tony told you, not every bit will be used for the key, and I will go through it again why. So we hope, so on average, because Alice and Bob will use random bases, we expect that in 50% of the cases, they will have the same basis. And those are the measurements which we can use to construct the key. So on average, we expect to have 8 photons in one session, or after one run of these 16 measurements. So, but we only need 5 bits to encode it. But that's even better, because according to the protocol, we need more bits to also check if an eavesdropper listened in, because an eavesdropper will appear by changing the bits. So we need to, so we have a secret of on average 8 bits, and we can use maybe 3 bits to check if actually someone listened in or not. But let's see how that will work out. Okay, so now the time is up for the experimental demonstration. Let's see if everything works out. So and oh yeah, maybe another thing which I can try is maybe the best position for this experiment to enjoy what's happening is to put you here. You should be able to see this polarizer. Yeah, I see my arm. Can you distinguish the two polarizers in the picture? Maybe, yeah.
Yes,
okay.
that can. The green spots, the cables.
Great. So let's see. On the also part of the fun is that I wrote down in the presentation which program to use for which step. So now I need to do it. Should be Bob receive key. Bob. And I know that we need to offset by around 105 degrees in the beginning. So now it's showtime, guys. Bob should now start sending I'm ready. Yeah, here's offset his measurement. And now Alice, if Alice starts her program, she will send a starting signal on the classical channel, and then the two polarizers should move synchronized. Huh? Maybe it didn't start. I have to see what's happening on Alice's computer. Nothing. Okay. Let's see if the magic happens. Okay, so both polarizers move from time to time. The thing is, if you have random sequences, they will not move all time. They will also stay for a part. But whenever they should move at the same time, it should look at least kind of synchronized. I'm not entirely convinced, but let's see if it suffices. Okay, we have, oh la la. Yeah, we have measurement results. So according to the protocol, what we need to do now is now Bob needs to send his basis. So again, we use the chatting. And Bob now needs to send his choice of basis. Let's see if it arrives on the other side. I know, because he's in sending mode. No. So we need to start the chatting again. No. Okay, we want to send this message. Okay, now I sent it twice, I think. Okay, so we take the first 16 bits of that, and that is the, oh, I just let him send again. Didn't understand. So there can always be problems in the procedure. Ah, great. Now I have 16 bits of information as Alice. So Alice can use this now for her key sifting. Okay, Python Alice key sift. So we will need this sequence and Alice sift key. And first we put in Alice's measurement sequence, which was this, but without the blank spaces. And what this is, and then we need Bob's basis choice. And now what this is doing is exactly what Tony showed you in the beginning. It checks if the first measurements are in the same basis. And if they are in the same basis, it will tell you if the two polarizers are aligned or 90 degrees off. All right. So according to what I have here, we have 6 bits of information, namely the first measurement. Does it make sense? Vertical and horizontal. Yes. Okay, cool. And then we should have the next measurement, for instance, at least should be in 2 different bases. Okay, so Alice was anti-diagonal and Bob chose to measure horizontal. Great, so that should be a different basis, and we discard this information because even though, because of the different bases, even though the photon arrived, we are not certain that they did, because they are in different bases. It could be because of the fact of the different bases. Okay, we have 6 keys. And now as Alice, I need to send this string back to Bob with the program chatting. And remember, this is already the key for Alice. So Alice knows this should be her key. And also the same should come out on the other side. That's enough. Okay. Now Bob knows which of his measurements to take and which ones to exclude with this string that Alice sent. So he's also done. Python Bob sift key. I hope it exists. Yes. And how do I use it? Okay, first the Bob's string and then the measurement result. And if everything went according to plan, we get the same string, the same 6 bits. First this string and then this string. So it cannot entirely work out. Okay, so the measurement didn't work. We entirely have zeros, but that is, so to say, the protocol. Okay, so there's a problem in the alignment, but imagine now that the measurement had worked, as I showed you here in the presentation. So these are the measurements which I have done yesterday to check if the experiment is still working. Okay, but as I told you, physics is when the experiments never work well. Okay, so imagine now that Alice and Bob know both independently that the key would be this one, the 0, 1, 1, 0, 0, 1. Then what they would do is they would share the first 0 publicly. So I could now yell over to Bob, hey Bob, the first bit is 0. And if he tells me 0, then we have some indication that no one listened in. Okay, and the other 5 bits we can now use to say if the cat is dead or alive. So with 1, 1, 0, 0, 0, 1. So let's translate again. So our key now is 11001. That translates into 1 as 16 plus 8, 0, 0, 1. So it's 16 plus 8 is 24, plus 1 is 25. So we need to shift by 25 according to our key now. So going ahead 25 letters in the alphabet would make an A into a Z. And the D, so after the Z we return to the A. That would make it into a C. So now, had the measurement worked as expected, we would have this key on both sides. And now we can use the chatting again. So that Alice can tell Bob if the cat is, what the cat actually is. Okay, and Bob now knows that the cat is Z, and with this head here taking the right measurement, he would have come to the conclusion that the cat is alive. So that's basically how one such measurement looks like, or how to make a key and how to share a secret. And so let's finish off. So with whom can we share secrets? So let's see how this is actually applied in real life. The current record distance for quantum key distribution based on fibers is 400 kilometers. So with such procedure, we can easily communicate with Sicily, as Tony showed already, but we can also go further. And now since exactly we can send entangled photons in space, we can even think about sending keys all around the world at one point. And how was it used? So this quantum cryptography scheme was already used in 2007 to secure the Swiss federal election in Geneva. So it's basically some technology which is already applied for a long time, because the people in the experiment, they can adjust their, or they can calibrate their experiment better than I can, apparently. And with that, I'm done. And I want to hear your thoughts and your comments. And if you are interested, there is some further reading. This is the actual link for the BB84 paper. And this is an archive paper, so you can access it even if you're not at the university. Everyone can access it. And this is, so I have to give credit to the people of this paper, because this experiment is based on this paper. So, and also in there you can read why this experiment, as I have done it, is not secure as a quantum key distribution. And that's basically the fact that we use a laser pointer, because the laser pointer will not emit single photons. So all the quantum physics, which I talked about, that's the big caveat, refers to single photons. So we have to use single photons, but for the more didactic purposes, I chose to use the laser pointer. And with that, I'm done. Maybe I take another video of an actual measurement that works and give it to you afterwards, but that's it.
Oh, thank you very much, Karl, for the great presentation, and also for the doing it live, to say running the risk of doing something live, because by doing something live, sometimes
there can be problems.
There may be problems, but this is a part of the experimentalist life. You are in between a theoretical and experimentalists. So well, it was my fault that we were running out of time, so we can leave a bit of space for questions and answers. In the meantime, I wanted just to say, while something to say eventually, is that Karl has just given an overview of the professionalities and of the knowledge that is needed in this field. So there are people that need to, because Karl set up the experiment on the table and he wrote the codes for the measurement. He set up the channel. So there is a whole ecosystem around quantum technologies on engineering, informatics, instrumentations, and all these will have in the next future many exciting professional opportunities. Of course, there is a lot of physics, because a photo detector, how you detect, how you build a laser, how do you maneuver a laser, is all part of physics. So then the recordings that we are doing, for who's interested, we will send back the recording, the link. So I congratulate myself with Karl, and considering also that this was the first time that we broadcasted it, because as Karl said, we were setting up this experiment since a long time. He was setting it up, and the idea is that the classes in the future will come, or for this event, they would come to the lab and see it in person, because it would have been more direct. Of course, Karl set up not 2 but 3 cameras in order to see all the parts. So he was in 3 places at the same time, and not only in 2. So a real quantum guy. So are there questions or clarifications, comments from the audience? Okay, if not, I can say that the first thing that I would like, because I will make a question to Karl about the experiment he performed. Can I make you a simple question for not physics?
Go ahead.
Not physics question. Suppose that in a school they want to set up such an experiment.
Yes.
Would it be possible, say economically, how much does the laser, the polarizer? I know that you dealt also with ordering the stuff for the experiment. So you may have an overview if some school, some teacher is interested in saying, oh, I like this, I like cryptography, there is mathematics, polarization. Can I put it up in my school? Would it be feasible?
Absolutely. So that's also basically what if you do didactics research, that's one part of your concern. And these guys in the archive paper, they are didacticists, whatever you call it. And they own, so I can go through the basic, basic stuff that you need. You need the laser pointer. I mean, those are 30 euros. Then you need the polarizers. So if you want to have two polarizers, they were 10 euros each on some big internet site, which I'm not going to mention. The Arduinos, which I use for all the coding and for all the managing of the simultaneous measurement are, so you need 4 for the setup, which are 15 euros each. So we're at 60 euros. The motors are 1 euro each. The only components, so the quarter wave plate, it has to be ordered for the right wavelength. Those are around 100 euros. And apart from that, you need an optical or an optical Schiene. How do you call that? One optical setup. So you need to set up everything in line. Either you have a table like we do at university, but at schools you basically only have the whatever you call a Schiene in English. But those should be at a school, to be honest. And apart from that, that's it. So realistically, I think okay, the photo detectors, but those are also not too expensive. Realistically, we are somewhere around like in the low 3 figures of euros. Oh. Below 1,000 euro for sure.
Oh, that's very good, because, and then we need the expertise, but you would be available to assist and in the setting up of the experiments. This could be a good idea.
Of course.
And also for schools, because the European Quantum Week is part of the Flagship, and in the Flagship there will be in the future calls for the schools for funding for quantum experiments. So setting up, buying the fundings for the setup of quantum didactic quantum experiments in schools. So keep this in mind should someone be interested in it. Very good. Of course, the Department of Physics can assist with knowledge and with bureaucracy in these calls as well. Very good. So if there are no further questions, I would thank everyone who took part. May I just ask, are you all students, or are you classes, or are you teachers, or are you other citizen, private citizen? Are you all in Malta? Because also this is something that I don't know.
I'm Antonia Vella, and I teach at the Junior College Physics. I'm the subject coordinator for the physics department in Malta, obviously.
Very good, thank you, Antonia. So you are with a class there. Hello, Antonia.
No, I don't have lectures at the time. That is why I followed you.
Ah, okay, thank you. No, because we wrote to the principal, and we were thinking that schools would take part with the class, say the teacher with the Zoom in the class, but I don't know. So, and the other ones are students, I guess, at this point, but Maltese. So
in fact, I informed all the students. I informed all the students so that if they were interested, and there were a few who were interested, and they were supposed to go in for this talk. I don't know whether they attended.
No. I was just wondering if the logistic was good, if the audio was good in different situations, because of course, if one is looking at the computer, probably everything is good. But if someone was with more
people, it was good. The problem was that at some times I got a message on the screen that my internet was fluctuating. So it was from my side that there was a problem. But it was very interesting, both of you. Well done. Thanks.
Okay, thank you very much. Thank you, Antonia. And let's keep
in
future initiatives. And I see that also Danielle is online, that is the science communicator of the Department of Physics, well, of the Faculty of Science, but mainly of the Department of Physics. I don't know if Danielle is online, if she wants to say a few words. Probably I caught her by surprise. So anyway, let's see. We are all here. So thank you again for your participation, and let's keep updated for future events. Thank you, Antonia.
Thank you very much for your interesting presentation.
Omag and the other participants that I see here from the
thank you very much.
Yes, thank you. Bye.
Bye, everyone. Yeah, and also if you want to get in contact with us, you can find us online. So feel free to discuss with us even afterwards. And also I would be pretty happy to show it off to actual students once the situation clears up. So keep that in mind.
Thank you.
Thank you.
Thanks.